Cosmologists have had to make a number of basic assumptions about the very nature of our universe. As there is only one universe, as far as we can physically know, there is nothing else we can compare it against. There is no control experiment you could do in a lab that gives birth to another universe in order to test one's theories by. The most basic of these assumptions are encapsulated in the cosmological principle. The cosmological principle, the foundational stone of mainstream cosmology, states that the distribution of matter throughout the universe is both homogeneous and isotropic when viewed from a large enough scale. In order to understand the depth of meaning in this statement, let's unpack it. So what do we mean by homogeneous? A homogeneous system has the same properties at every point. It is uniform without irregularities. A large region of a homogeneous universe looks approximately the same when compared to any other large region of the universe. Another way to state this is to say that the same laws of physics that we experience here on Earth are the same throughout the entire universe. Thus, spiral galaxies all tend to look the same, because the same laws of physics that made our own Milky Way galaxy the spiral shape it is, also by extension, is responsible for the shapes of all the other spiral galaxies. And what do we mean by isotropic? An isotropic universe would look the same in all directions. Point a telescope one way, peering into the distant universe, and the picture would look very similar to another picture taken of the distant universe if the telescope was pointing in another direction. In medieval times, the assumption and belief was that the Earth was the center of all creation. It was considered by man to be the center of God's creation. Copernicus overturned this belief that the Earth was not the center of the universe when he showed that both it and all the other planets in our solar system orbit around our Sun. The Sun, in turn, holds no special place or orientational direction in our galaxy as compared to all the other stars in the Milky Way. Our place in the universe is one of complete random chance. What this means for physics is that the same experimental results we record here will be the same regardless of our location in the universe. Stars and planets in the furthest galaxies are made of the same stuff, the atoms shown on our periodic table. In effect, the cosmological principle says that look far enough out into the depth of the universe and you'll see the same picture pattern over and over again. A picture of multiple galaxies whose count falls inside a predictable range. Randomly select a sufficiently large enough volume of space within our universe and count the number of galaxies occupying it. Repeat this process. Again, randomly select a sufficiently large enough volume of space and again count the number of galaxies inside that volume. If the distribution of matter throughout the universe were homogeneous and isotropic, then the number of galaxies found in any sufficiently large enough volume would roughly always be the same, regardless of the volume's location. Meaning that if I continued repeating the same process of randomly selecting a sufficiently large enough volume and recording the number of galaxies inside that volume again and again, I would expect its count to fall within a normal distribution. The importance of the cosmological principle, as stated as such, is that the observations and experiments we do here on Earth would be the same elsewhere in the universe, and when we look far out into the observable universe, we do see the same distribution of galaxies from nearly all over. I say nearly, as we'll look at a number of new discoveries that have caused some cosmologists to question this principle. When we look out into space from here on Earth, we look back in time. The furthest moment in time we are able to look back to is the light emitted in the afterglow of the Big Bang event, namely, the cosmic microwave background radiation. Anything beyond this is beyond our sight. So in order to make statements about the larger universe beyond our vision, we need to make a number of assumptions, and that is the point of this cosmological principle. Such a statement, in light of the universe being flat, is that the universe is infinite, that it has no edge, I will argue otherwise. I mean, how can it be infinite, with no edge, if the universe is finitely old, 13.6 billion years or so? Rather, this appearance of isotropic and homogeneous arises from the rotational vortex of the jet that is our universe, as I'll demonstrate using a nice hot cup of tea. Another problem in this definition, that the distribution of matter is homogeneous and isotropic at a sufficiently large enough scale, is the sufficiently large enough scale. What is sufficiently large enough? I've discovered an ever-increasing number of definitions of sufficiently large while researching this piece, and in an infinite universe, sufficiently large what can be conveniently expanded to any size. One definition of sufficiently large, coming from Wikipedia's page on the cosmological principle, is that it is statistically homogeneous on scales larger than 250 million light-years. Another interpretation from the Sloan Digital Sky Survey suggests that the galaxies smooth out above 100 megaparsecs, or 326 million light-years. A very important factor to consider when applying the cosmological principle is the evolution of galaxies in relation to each other by the force of gravity. It has been discovered that galaxies under the influence of gravity clump together. These clumps form groups. In turn, groups of galaxies come together to form clusters. And lastly, that these clusters of galaxies group together into superclusters. This clustering of galaxies evolves over time, meaning that galaxies whose initial distribution was homogeneous and isotropic in the very early universe came together to form clusters and then superclusters over time. Looking out at those galaxies closest to us, we should see the formation of clusters and superclusters. But for those galaxies in the very early universe, at the limit of our vision, then we shouldn't see this. Rather, the distribution should be homogeneous in the pictures of the far distant and early universe. With all that said, what makes me think that these assumptions are in fact false? The cosmic microwave background radiation, after all, was found mostly to be isotropic and homogeneous, with little variation, reinforcing the belief in the standing cosmological principle. Well, this last statement about the microwave background in regards to being isotropic is strictly not true. Collectively known as the axis of evil, a series of very improbable alignments to Earth and our solar system were seen in the cosmic microwave background radiation. For instance, the CMB is slightly cooler when viewed through the top half of our solar system and slightly warmer on the opposite side. It's not much of a variation, just a handful of microkelvin difference, but it's measurable and definitely there. Initially written off as a statistical fluke when it was first observed in the WMAP experiments, the same observation was made again in the Planck mission. Two independent experiments recorded the same result, passing a major hallmark of scientific discovery, independent reproduction of the same unexpected result. Although we shall look at this series of anomalies, known as the axis of evil, in much greater depth later on, it is a result that flies directly in the face of the assumption that the universe is isotropic. That is, both Earth and the Solar System have this improbable alignment to various anisotropies identified in the CMB, and this result has been reproduced in two independent experiments. I do not believe this improbable alignment is some mere random fluke of nature. Rather, it is a property of nature whose invisible underlying framework we shall endeavour to explore.